Hello, folks. This is the unit on Kmeans clustering as part of machine learning and cloud services, which has three parts. And we're in part B of part one, which is an introduction to Kmeans. And I'm Jeffrey Fox, the instructor, and it's currently April 2019. And we will later on look at some other clustering algorithms in uh, part three of this collection of on machine learning and cloud services. K-means clustering. Surprisingly, one of the most successful heuristics there is. So simple. All right, so here first some rather more general remarks of on this issue of machine learning. We have supervised learning and unsupervised learning, and clustering is a nice case of unsupervised learning because most of the huge successes like deep learning are supervised. You have to have labeled data. At least for the huge successes, we had to have labeled data. There is deep learning without labeled data. So there you have a set of labeled data. We actually saw that earlier with regression. Regression certainly uses labeled data to predict those alphas and betas. And all of those regressions were typical labeled data, and there's lots of examples where you have data such as those on. If you're trying to predict whether a student would be admitted, you would just you have so much data from the past, it should be easy to match your student to previous students, or and by looking at as a function of SATs and grades and things like that. And then we just make a model, and then we label the new data by the model to predict whether our kids will get to go to university. Now, unsupervised learning, we may wish to uh, divide them into groups by their location or by their color or something like that. There was no previous labeling. We have to invent the labeling, and we don't know how many groups there are, maybe. And we definitely don't know what the colors are. So, and the way we do this is in almost all these things in machine learning, you have to define either a space in which they live, a geometrical space like space and time, or 2 dimensions or 3 dimensions, or you invent a space, like you invent a space to describe the color, or invent a space to describe the speed of the car, or things like that. So unsupervised learning always requires typically some distance measure. And as we'll mention from time to time, there are two cases. One where you actually have a true vector space, where you have points in the space and define scalar products and all those other nifty things you have in spaces. And the other case is where you just have distance, where you can't take scalar products because maybe the data, like in gene sequences, is not properly aligned, and so you can't directly do a scalar product. All right, so unsupervised learning is challenging because it's all from scratch. Now, in clustering, if you have nice separate clusters, then actually from scratch you can say, well, I'm sort of cheating. It's really supervised because you have the position. It's just that we've not defined the clusters, and it's not so trivial to find an algorithm which reliably finds clusters even when they are spatially separated. And as we'll discuss, there are many problems when they're not even spatialized, that they aren't even separated. And these are often pretty compute intensive. It's not just calculating, like in regression is a very simple algorithm. That's not very compute intensive. And we will often stress that there is no universal method. The reason why data scientists get jobs is they have the intuition to know which algorithm to use for which problem. And unsupervised learning is pretty important in spite of the challenges. And there are many probably new algorithms waiting to be discovered. All right, so K-means clustering finally. We have data points, n. little n. Clusters, little k. In a few cases, k is known. Other times you guess it, or else you actually feed in a different piece of information, a useful piece of information as the size of the cluster. If you know, say, because the reason they're clusters is there's a real point and then you have a scatter of measurements about that point, then the size of the cluster is related to your measurement error, and you may well know your measurement error. Alternatively, you might be able to just know there is a measurement error, but you don't know what it is. Then you have to find the measurement error. In case of gene sequences, that's sort of typically a situation. So here we, in Kmeans, we actually define the centroids, which are the same thing as cluster centers, and we just do everything iterative. It's a heuristic, and it's also a greedy heuristic. And most of the world's successful algorithms are greedy heuristics, namely, you guess something, then you take where you are, that's a point in some abstract space maybe, and then you move to another point in the most obvious fashion possible, which makes it look better. And in the case of K-means, you take a bunch of centers, you take a bunch of points, and you assign each point to the nearest center. That seems sort of obvious, isn't that right? Then you calculate new centers and iterate this algorithm. So that's it. That's K-means. And every point will get labeled. There are all sorts of little subtleties and cleanups and things, because you might have isolated points, just one point on its own. Because a well-known feature of clustering is if you have n points, there is always a solution with n equals k. Then you can just make every point one cluster. That's a hugely successful clustering algorithm of absolutely no value. But it has some measure of perfection, which is infinite, because the distance between the center and the point is 0 for every case. But that's not what we want. We want smaller number of clusters, and we'll have some points which are not directly on the center. They'll be away from the center. So here we come to Wikipedia, which is often has useful information. And here we have 12 gray points, and we have 3 centers, and here are 3 initial values for the center: the blue center, the green center, and the red center. So now we apply this algorithm associating with each center the nearest point. So the red center is off in left field, and we just get 1 point. The green center has lots of points, has 5, and so does the blue center. Actually, the green center has 6, and the blue center has 5. And now there's actually an interesting feature which shows how you can make mistakes. If this red center was a bit further away, like up here, then there will be no points near it. All the points would be nearest a blue or a green. And actually, that often sometimes happens. You get rid of such glitches by choosing multiple starting points. Like in the classic Python algorithm, you use 20 different starting points and choose the best answer from those 20. All right, so now we take the original locations, which are these things with dotted edges, and we move them to their new position, which is, in the case of this one here, it's actually on top of the point, because there was only 1 point in this cluster. And this center here actually doesn't move very much. It moves from here to here, and nor does the blue, because the blue and the green were right in the middle of lots of points, and you associated the points with those guessed centers, and they don't move very much. Then we do it once more, and after we've done it once more, we'll find a convergence, because if we keep rerunning it, we'll always get the same answer. If we now do a rerun with this, and this as the center, we will find that the red one grabs a point. This point here wants to go here. So we end up with a red cluster with 2 points, a green cluster with how many points would it have? 1, 2, 5 points, and blue cluster with 5 points still. And these are the new points. The blue hasn't changed, the red has moved down, and the green has moved down. All right, so that's the answer. All right, so actually I should have said I commented as well. I think the Wikipedia picture is not correct in the way it represents centers, but I corrected it with those stars. All right, here we mathematically state the problem. We have a set of points, little n of them. We have a set of clusters, little k of them, and we randomly choose the cluster centers, or we intelligently choose them. I mean, random is not terribly good. If you know all the points between 0 and 1, you wouldn't want to put a center at 20 units away from that. And here we have this wonderful algorithm. For each point, find the nearest center, assign the point to that center. Then you take each of the clusters and you take all the points assigned to the clusters and you calculate the new center as the mean of all the points. And then you stop when the cluster assignment doesn't change or the assignment is so small. In a real big problem, you will just stop when the change is small enough. Because you have some measure of how well accurate you want the centers. And so when the centers are all changed by less than that accuracy, you can also stop. So there's some stopping criteria which depends on the details of how accurately you want the answer. Remember, in the case of data analysis, accuracy is a little tricky because you don't really need answers which are more accurate than the quality of the data you have. All right, so what's good and bad about K-means? Well, K-means is applicable in any case where you have, as I've described it, a vector space. There is a variant which I have a very good implementation of, which only needs you to have a distance defined. So there is a K-means with distances only. And it is very easy to understand and it's very easy to implement. And as we'll mention towards the end of these, actually at the end of this unit, it is easy to run in parallel. It can be computationally intense, especially if the points are high dimension. However, that computational intensity can be addressed in many ways. The easiest is to parallelize it because the parallel algorithm is so simple. There's a fellow called Elkins who invented a clever algorithm to say that you didn't really need to look at all those comparisons if you can use the triangle inequality to say there's no chance that this point be associated with a particular center. That's useful in high dimensions. High dimensions are the trickiest case because if you want to calculate distances in a space of dimension big D, there are big D. You'd have to do big D operations. You'd have to do xi minus, well, if we're looking at distances from centers, xi, the x component, the x sub 1 minus center sub 1, x sub 2 minus center sub 2. So you have D of those, then you square each of them, and you take the square root. So if the D is, the computational complexity grows like big D, the dimension. I pointed out we have to be a little clever about initializing the centers. It's probably not best to do them randomly, but to do them intelligently. And even more seriously, we don't know what to do for K. The algorithms I tend to use, which I have some results of, they actually do not require you to guess K because they use the size of the cluster to determine K. And noise can produce lots of trouble. And you can get lots of tiny clusters if you have a scattering of points which really don't cluster at all. Because in a real problem, you'll often have some maybe clusters, but then as well as those clusters, you just have some measurement errors which give you a bunch of junk. And you need to be able to cope with that. And K-means doesn't cope very well with such things. It doesn't have a junk category. Some of the algorithms I have junk categories. All right. So the improvement, which I will stress, is visualization. You need to look at the answer. Does it look correct? The human eye and the human brain are very effective at telling you whether there's a problem. We need to not do too many clusters because they'll just end up creating irrelevant noise. We can, if we like, remove noise, and I must admit I've never done that. I just do algorithms which are noise insensitive, and that's one of these improved clustering algorithms which we will not discuss, but we do note they, of course, as they're improved, will tend to use more computing time because they have sophisticated algorithms. If you want to go applications, so if we're Amazon and we want to predict and you go in there and buy a blue frog, Amazon will try to suggest other things you want to buy. And so it will take the space of items and it will cluster in that space and see what things look like blue frogs based on some. They will take every item in their store and they will assign it features. They will calculate the distance from that features, and then using that distance they can do some clustering, and there will be a bunch of things like pink frogs or blue hippopotami which lie near the blue frog, and they will suggest that you buy those as well. There's lots of applications of clustering in the spatial domain. You can look at, you can find ghettos or clusters of people of a certain type living in the same place. And I will show you many examples of DNA clustering, which allows you to find families and species. And actually, the area where I first studied this is a different type of one, where the case of the DNA sequences is evolution that's caused the the fact that not all sequences are the same. In the case of, I usually use the case of an earthquake. So if you're trying to measure the length of a rod in an earthquake, that rod is jiggling, and it's going to be hard to measure. And depending on the strength of the earthquake, you're going to get more or less measurement error, and that will produce a cluster of points around the real value. And let's say you had, you might have 16 items which you're measuring, and you'll get 16 clusters of points around that, the true value of each of those 16 items. So that study of possibility